lecture on the Laplace transform. Begin by reviewing the improper integral. That's how the Laplace transform is defined. And then we'll go on to define the Laplace transform. Here's how we define the improper integral. We have a function that's defined on all non-negative real numbers. That is the interval from 0 to positive infinity. So notice if we drew that, that would look like a ray. The improper integral from 0 to infinity is defined as the following limit. Integral from 0 to infinity of f of x dx is equal to the limit as r goes to infinity of the integral from 0 to r of f of x times dx. The improper integral is said to converge if the limit on the right-hand side exists. So if this is a limit of definite integrals, so these will always exist provided f is any continuous function on the interval from 0 to infinity. And this limit will be a limit of definite integrals, that's a limit of numbers. If this limit exists, then the improper integral from 0 to infinity of f of x dx is said to converge. So here's an example of an improper integral that does not converge. Let's look at what does it mean to evaluate the improper integral from 0 to infinity of 1 over x plus 1 dx, or to determine equivalently whether or not it converges or diverges. This means to evaluate the limit, if it exists, from r to infinity of the definite integral from 0 to r, 1 over x plus 1 times dx. Capital F of x is natural log of absolute value of x plus 1, which is an antiderivative of 1 over x plus 1. If you plug in r, that's the upper bound of the integral, and 0, that's the lower bound. Plug in 0 to the antiderivative, you get 0. If you plug in r to the upper bound, you get ln of opposite value of r plus 1. If you notice, if you take the limit then, as r goes to infinity, you get infinity. Infinity is not a real number, so this limit does not exist. It just doesn't exist in the special way by which the function blasts up and blows up to infinity. So this definite integral, the definite integral from 0 to infinity of 1 over x plus 1 dx, does not converge. Now here's an example of an improper integral that does converge. If we look at the integral from 0 to infinity of 2 over 1 plus x squared dx, pull out the 2 from the integrand, that's the same as the 2 times the limit as r goes to infinity of the definite integral from 0 to r, 1 over x squared plus 1 times dx. Capital F of x is arctan of x. This is an antiderivative of the function 1 over x squared plus 1. F of 0 is 0. F of r is arctan r. If we look at the limit of the difference of these two values as r goes to infinity, this is just 0, so it's not going to affect anything. But limit as r goes to infinity of arctangent is equal to pi over 2. And that's because if you plug in larger and larger numbers for inputs into arctangent, that means you're looking for an angle whose tangent is larger and larger values. And the only way to get angles between negative pi over 2 and pi over 2 whose tangent is huge is for that angle to approach pi over 2. In that case, notice pi over 2, at the angle of pi over 2 radians, sine is 1, cosine is 0. So 1 over 0, that doesn't exist. So in the particular, if the denominator is approaching 0 and is remaining positive, and the numerator is approaching 1, that value is approaching positive infinity. So conversely, also limit as theta goes to pi over 2, the tangent of theta is equal to infinity. So this limit is 2 times pi over 2, just this limit is replaced with pi over 2, and 2 times pi over 2, of course, is just pi. So this definite integral, or I'm sorry, this improper integral, which is the limit of definite integrals, is equal to pi. Now, we're in a position to discuss Laplace transform. The Laplace transform takes a function and it spits out another function. And the way it does that is by feeding the function into the integrand of an improper integral. And in the integrand, it doesn't just be itself, because then it most likely will not be defined, but you need to multiply by e to the minus s times x. And the reason for this is that e to the minus s times x, that's exponential decay. Exponential decay is very fast. So that's going to mean most likely if fx is most continuous functions, is pretty much any continuous function, this is going to converge. This improper integral is going to converge for some s naught. And it turns out to be the case that if it converges for some s naught, it also converges for all s that is larger than that s naught. Laplace transform, denoted L of f of x, is given by the following function. Integral 0 to infinity of f of x times e to the minus sx dx. So it's just written in. So here, we just interchange the order of f of x and e to the minus sx. Multiplication, of course, is commutative, so it doesn't really matter. And like I said, L of f of x is a function of s. It takes one function to another function. And that's just a convention. X and s are they're just notation. So L of f of x, that's just to denote, okay, the original function. S means that's the function we obtain after we apply the Laplace transform. Laplace transform is linear. That means if you feed it the linear combination of two functions, c1 times f plus c2 times g, you can pull these constants out and becomes c1 times L of f plus c2 times L of g. It's also one-to-one. If L of f is equal to L of g, f and g have to be equal. And because it's one-to-one, it has an inverse. L to superscript -1, where if L of f is equal to capital F of s, L inverse of capital F of s is equal to the function f. L inverse is linear, meaning L inverse of a linear combination of two functions, c1 times capital F of s plus c2 times capital G of s, can pull out the constants and add up the inverse evaluated at those two functions. L of y prime is negative y of 0 plus s L of y, L of y double prime. So all these previous four rules had to do, rules or properties of the Laplace transform just had to do with its linearity and the fact that it was one-to-one and had an inverse. This is what happens when you feed it the derivative of a function. It's actually possible to write the Laplace transform of the derivative of a function as negative the value of the function at 0 plus s times the Laplace transform of the function. And the same thing for L of y double prime. So Laplace transforms amazingly takes the derivative of a function, and you can actually pull out this variable s. So this is a way of rewriting Laplace transform of the derivative is just rewritten as the value of the function at 0 plus a variable s times the Laplace transform of y, Laplace transform of the original function. There's no derivatives on the right-hand side. The same thing for L of y double prime. Minus y prime of 0 minus s of y of 0 plus s squared L of y. You only get an L of y term here. There's no L of y double prime. And we'll see in the next slide how that's applied to solving ODEs. Here's a table of Laplace transforms. And this is important because you can also go the other way. If you look at Laplace transform, well, its inverse is going to be, say, we're given the function 1 over s, its inverse is going to be k. We're given the function n factorial for s to the n plus 1, its inverse is going to be x to the n. We're given the function 1 over s a, 1 over s minus a, its inverse is going to be e to the ax, and so on and so forth. We're given the function 1 over s squared plus 1, its inverse is going to be sine of x. Given s over s squared plus 1, its inverse is going to be cosine. We're given, say, 2s over s squared plus 1 squared, its inverse is going to be x times sine of x. Let's see how this plays out in solving an ODE with a Laplace transform. Let's solve the ODE y double prime plus y is cosine x subject to initial conditions. Y of 0 is 1, y prime of 0 is negative 1. Step 1 is to take the Laplace transform on both sides. L of y double prime plus L of y is L of cosine of x. The next step is to simplify the Laplace transform of each term and plug back into the original equation. L of y double prime is negative y prime of 0 minus s y of 0 plus s squared L of y. L of cosine of x, you can look back at the previous table, is s over s squared plus 1. So the equation becomes 1 minus s plus s squared plus L of y is equal to s over s squared plus 1. Look, no derivatives. That's the amazing property of Laplace transforms. You can just apply them to a linear ODE. Now, this only works for a linear ODE. It will not work for a nonlinear ODE. But for a linear ODE, you can apply it to both sides. And on the left-hand side, you just get something that just involves L of y. And you can solve for L of y as a function of s. And then you can pretty much guess the next step. That's going to be solving for L of y and then taking the inverse Laplace transform. When you take the inverse Laplace transform on both sides, inverse Laplace transform is linear, so we get inverse Laplace transform of s over s squared plus 1 squared minus inverse Laplace transform of 1 over s squared plus 1 plus inverse Laplace transform of s over s squared plus 1. And if we look at each of these terms, well, inverse Laplace transform of s over s squared plus 1 squared is 1/2 x times sine of x. That's just linearity. Inverse Laplace transform of 1 over s squared plus 1 is sine x. Inverse Laplace transform of s over s squared plus 1 is cosine x. We plug each of these functions into the formula for y in step 4. We get the following: 1 over 1/2 x sine x minus sine x plus cosine x. And this is a solution. So notice that actually was a lot quicker, just looking that up in the table, applying Laplace transform to both sides, solving for L of y, looking up, take the inverse of the functions and look up the Laplace transform on the table. That's a lot quicker than, a method of variation parameters, method of undetermined coefficients. It becomes a lot quicker. We just got these three terms just from taking the inverse Laplace transform and looking up those formulas in the table. And now we have these terms. We didn't have to go through, okay, now we have to solve for u1 prime or u2 prime, or solve for a times x sine of x, and then to differentiate and so forth. Okay, so we'll go on more properties of Laplace transform in the next lecture.